Thank you for the introduction. I'm glad you said the title and don't have to anymore. Hi everyone, thank you all for coming. I am Mathieu Nancel. I'm a permanent researcher at INRIA Lille in France. And this is a joint project between two research groups from INRIA Lille, the LOCI group that I'm a part of, and the NOAA group that deals with optimization and control theory. So, as the title states at length, this is going to be about input prediction. But first, I have to talk a little about latency. Most interactive systems have a delay between user input and the corresponding interface feedback. That's called latency or lag. Latency has a number of sources, both hardware and software. For instance, the time it takes for the input to be recognized, or the time it takes to render the visual feedback. The sum of all of these intermediate delays is typically between 50 and 200 milliseconds for direct touch. That's not much, but previous work in SIGCHI have shown that delays as low as 10 milliseconds still cause pointing performance to degrade, even when that delay is not noticed by the user. And we can't just wait for hardware to catch up with latency. Hardware improvements do help, and they will keep helping with that issue, but it will probably not solve it in the foreseeable future. For instance, most displays are refreshed every 15 milliseconds or so, which is fine for the human eye, but that's already above the performance threshold found in previous work. And some of the sources of latency depend on the software complexity of the task at hand. For instance, very rich visual feedback in 3D video games. And we expect that as hardware keeps improving, that complexity will keep increasing as well. That's called Blind's law. So there is a part of latency that hardware can solve, and for everything else, there's input prediction. Input prediction is a software process that consists in displaying visual feedback not for the last detected input, but for an input that is expected to be detected in the near future, corresponding to the finger's current location, hopefully. For touch, that means to extrapolate or forecast or predict the trajectory of the user's finger in order to estimate the current finger location. There's already a quantity of research on such prediction methods and also a number of patents from major players such as Microsoft, Apple, Samsung, and so on. Some are already implemented in commercial products. Existing methods are based on Taylor series, Kalman filters, curve fitting, specific heuristics, you name it. However, all of these existing methods, they actually only correct a small fraction of the total latency, in the order of 5 to 30% in the best cases. This means that most of the adverse effects of latency on performance remain, even when prediction methods are applied. And that is because the further the extrapolation, the higher the chances of prediction errors. So, okay, up until now, those were exactly the same slides as I presented at UIST 2 years ago. Same problem. Our contribution then was not about a new input predictor, but about how to evaluate those predictors. Among our contributions, we identified typical prediction side effects as they're perceived and stated by the users. They are in increasing order of disturbance, the lateness of the prediction, a spring effect, that is basically the cursor playing yo-yo around the finger, over-anticipation of the predictor, wrong orientation, that's the prediction going in the wrong direction, and finally, jitter and sudden cursor jumps. We also found that error metrics based only on distance, which are standard to evaluate input predictors, they are not that good at modeling what really bothers users. These metrics confuse different types of errors, and in some cases they can even lead to favoring them. For instance, in our results, root mean square error, it was negatively correlated with perceived jitter, meaning that if you select a predictor on the basis of a low error, you can actually increase the jitter of your predictor. So we then formulated a set of metrics that fit those user-stated side effects well, using only the geometric properties of the trajectory and of the predictor. And finally, we made our metrics and the gestures that we collected available to use for other researchers. Now, what we've done in this paper is to devise a new predictor that makes use of those findings, and it's based on 3 observations. First, the typical derivation methods that are used in SIGCHI, they remain rather simple, and they can be highly subject to noise, to imprecision, or to additional delays. Our second observation is based on our experience with implementing and using many different predictors. Basically, because input frequency can be inconsistent and because of natural variations in human movement, predictions, which are typically extrapolations, they become more noisy the further we predict. And finally, in our past results, jitter was a side effect rated worst by participants, and it was reported less often for fast movements. So either there's less jitter when we move fast, or it's less noticeable. And on the other hand, latency, this phenomenon of lateness, it's less noticeable at low speed since the visual feedback remains close to the user's finger. So prediction is less necessary at low speed. So for those reasons, we posit that prediction should be damped at low speeds. Based on these observations, we designed a prediction algorithm that works in 3 steps. First, it calculates the recent time derivatives, and it calculates a first extrapolation like most predictors. However, in our case, we use the current state-of-the-art of online derivation methods from the field of control theory. It is more robust to input noise than classic methods, and it can be computed very rapidly, so it does not introduce extra delays. It has 3 parameters that are defined offline through optimization, based on a small set of input data, and only once for any given device. And it also has a general parameter that can be defined by hand, and that sets the trade-off between derivation accuracy and computation time. In the second step, our algorithm progressively turns off the prediction when the user moves slowly. The core idea is that whenever the input speed is below a certain threshold, there is no need for prediction. However, interrupting the prediction suddenly might cause the cursor to jump back. So we added an exponential weighting function that smoothly turns the prediction off or on, and whose parameters can be adjusted to the task or to the user's preference. Finally, our algorithm smooths the predicted points with minimal additional delay, using 2 one-euro filters, one applied to the distance from the prediction to the last detected input in order to remove low-frequency oscillations. And the second filter is applied on the predicted positions themselves to remove the remaining noise. And you can find more technical details in the paper. So we evaluated our predictor in 2 steps. First, we ran a benchmark evaluation using strokes we collected in a previous study, so we could quickly calculate error metrics on a large data set. Then we gathered subjective feedback by asking new participants to test our predictor and others in different tasks and with different amounts of compensated latency. So, in the first evaluation, we reused the 6,000 strokes that we gathered for our 2016 study. They involved 3 different open tasks, and the strokes lasted 50 to 6,000 milliseconds. We tested 6 predictors from industrial patents and from the literature, 4 of which were in our previous study, and we added the double exponential smoothing predictor by Joseph Laviola, as well as our candidate technique, obviously. And finally, we tested those predictors on 8 error metrics, 2 that are purely distance-based for reference, and the 6 metrics that we developed in our previous work. So, from all that, first, here you see the amount of error on the y-axis and the amount of compensated latency on the x-axis. And our predictor is highlighted with dashes, if you can see it. So, first, on those 2 traditional metrics, based on distance only, we found that our predictor fares reasonably well. That is, it's not best, but it fares among the best, especially at high levels of latency. However, as we showed in that previous paper, those distance metrics, they hide a great deal of complexity about what bothers users. So if we look at our side effect metrics, we get possibly a somewhat clearer picture. So here the y-axis becomes the probability to observe a given side effect as modeled by our metrics. So our predictor fares best, significantly, for jitter and jumps. And it's among the best, it's a tie, for over-anticipation, spring effect, and wrong orientation. An interesting observation here is that the pros and cons of other predictors can vary greatly. One can be among the best for over-anticipation and simultaneously among the worst for jitter. Ours, on the other hand, is behaving fairly consistently across metrics. For lateness, finally, all predictors remained in the same ballpark of probability, and ours were ours was consistently worse than first-order Taylor series, curve fitting, and heuristics. However, as I said, they all remained within the same 5 to 15% probability range. Now, you might wonder, well, this is about latency compensation. What's the point if users still observe some lateness? My answer to that is lateness is what should remain when you are unsure how to predict. Here I overlaid the ratings that participants gave to each of those side effects in our 2016 study, from 1 to 5, 5 being unusable. And as you can see, lateness was actually the least problematic of those, and jitter and jumps were the worst. So what this shows is that our predictor minimizes, in theory, the side effects that matter most. Now, in order to confirm those theoretical findings, we run a new study to check whether our predicted side effects match real use of our predictor. We asked 9 participants to use the same predictors as in the benchmark study on 3 tasks: dragging an object around, drawing a shape or free drawing, and we added writing as a typical touchscreen task that can be harmed by latency. And finally, we tested 5 levels of compensated latency from none at all to 64 milliseconds. After each condition, so a predictor, a latency, and a task, we asked participants for a usability rating ranging from nothing to declare to that is just unusable. We also asked them whether they would consider using this predictor in real life for this task and this amount of compensation in their daily, personal, and professional use. And finally, when they said that they would not consider using it, we asked why in terms of side effects. So our first clear finding is that the TurboTouch predictor was clearly and significantly preferred by our participants. And it's interesting to see that our predictor, so here in black, starts to distinguish from all the others, starting from 32 milliseconds of latency compensation, which is more than what most existing commercial predictors dare to predict. Usually they stop around 16 or 20 milliseconds. We can also see that the usability ratings of our predictor at 48 milliseconds and below remain in the range of most others at 0 and 16 milliseconds of compensation. Second, we found that participants declared that they would not consider using our predictor less often than all other predictors. So this graph represents the number of times, so number of conditions, in which participants answered no to the question, would you use this in your daily use? So the lower, the better. Again, we can observe that the levels 32 and 48 milliseconds received similar feedback as others with less compensation, indicating that up to 48 milliseconds can be a realistic level of compensation in real use. Finally, and happily, we found identical trends between the results of the benchmark study and our participants' feedback. In particular, jitter, jumps, and spring effect were seldom reported with our predictor, and reports of over-anticipation remain low until 48 milliseconds of compensation, and lower than all other predictors. And we encourage you to check the paper for more details about which side effects were reported by the participants. So before I conclude, we see many potential directions to expand that work. The first one is, well, this works well, but in which part is it thanks to the derivation method, the damping, and the filtering? We would like to explore systematically the effect of each of these steps, because some of them could be applied to other existing predictors and improve them as well. We would also like to compare our algorithm to other existing predictors that at the time of these studies we could not successfully replicate in our software. And finally, we plan to try this predictor in other contexts such as indirect pointing and virtual reality. And I'm a little short in time, so I will just show my summary. I will just say that I'm looking for PhD students to work with me at INRIA Lille on the topic of time travel. Come talk to me if you're interested. And I will thank you for your attention, and I will now answer your questions if you have some. Thank you very much.
Thank you very much. I will remind you that there is a microphone in the back and a microphone over here. And Dan, yes.
At Ashbrook University of Copenhagen.
Hi.
I might have missed it. How many previous points do you need to get a good prediction for the next point?
Good point. I think it's more in the. I don't know. I cannot tell you. That's in the specificities of the derivation estimator. I would say. I would say 4 to 6.
Okay, so not very many.
No. I mean that's actually the core point of this derivator from the control theory. This is really meant to work in real time and as quickly and efficiently as possible. So I mean that's a topic that they've started studying way before us.
Right.
So
Yeah. Okay. Cool. So one other question then. You mentioned you want to try this with different contexts in VR or with indirect pointing. Does your intuition tell you that it's just going to work, or that you'll have to screw around with it a lot?
My intuition tells me that it's a really interesting direction to explore. No, I mean, I was given a really good example during the demo sessions. My first intuition was it would be good in VR because of motion sickness, for instance. And this is it's hard to know if it's going to work as well in rotation than with touch. But someone else talked to me about this notion of giving a haptic feedback on time and not once you've gone through the thing. And this would just translate what we did from 2D to 3D. And I think that's something we can confidently count on. Yeah, I would be confident that this could work.
Cool. Thanks.
Thank you.
David Martin, Nareva. Inking is a more significant problem for latency. Did you experiment with that? Does it apply? Does your technique apply there?
By inking, you mean drawing and leaving a mark?
Drawing on a touch display.
Yeah. So yes, this was actually one of our tasks. A rather interesting thing that we found was that so that was in the previous study. The side effects that people reported were, I mean, some of them were actually strongly dependent on the task. Like for the exact same geometrical errors, geometrical behaviors, people would actually notice some when there's a mark following you around than when you're moving an object whose position is only the prediction. So I mean there's really interesting things to be observed about how the task and especially the visual feedback of the task affects perceived side effects. And so right now our predictor is not defined specifically for a task or another, but there's certainly a way to apply those different findings to a specific task if one wanted to.
Thank you.
Thank you.